All right, class, welcome. Today, we're going to break down one of the most important tools in all of modern medicine and physics, the X-ray tube. Seriously, for any of you looking to understand medical imaging, this is ground zero. This is where it all starts. So let's just start with a fundamental question, one that totally revolutionized diagnostics and how we see what's happening under our skin. How is this even possible? It's not magic, I promise you. It's just applied physics, and it is incredibly elegant. Well, the answer is this amazing piece of engineering right here, the X-ray tube. This thing is the absolute heart of modern medical imaging, and really getting how it works is crucial for any of you studying physics or medicine. Okay, let's dive in and see what makes this thing tick. To really understand how it works, we need to look inside. We have to meet the key players that make this whole thing possible. Think of this as a quick anatomy lesson for the tube itself. First up, we've got the cathode. Now, this is the negative electrode, and I want you to think of it as the starting line for the entire process. This is where our little projectiles, the electrons, are loaded up and ready for launch. Now, the physics of how those electrons actually get free is just fascinating. It all happens through a process called thermionic emission. Basically, we heat a tungsten filament to an insane temperature. We're talking over 2,000 degrees Celsius, until it literally starts boiling electrons right off its surface. This creates a charged cloud, kind of like water boiling into steam. Then a focusing cup wrangles that cloud and aims it precisely where it needs to go. Okay, so if the cathode is our starting line, then the anode is the target. It's waiting at the other end of this tiny little racetrack. As the positive electrode, it has this massive voltage difference that yanks those negatively charged electrons across the gap. The anode's job is, well, it's brutal. It gets bombarded by a constant stream of high-speed electrons. That's why it's also made of tungsten. It has a super high melting point, and it's great at handling heat. And here's the crucial part. This whole process is incredibly inefficient. Get this, over 99% of the energy from those electrons becomes pure heat, not X-rays. To deal with that intense heat, a lot of anodes actually spin at incredible speeds, sometimes up to 10,000 RPM, just to spread out that thermal load and stop the target from melting into a puddle. So, we've got our components, right? We have a source of electrons and a target. Now, let's move on and see how this all builds into a system that can actually generate X-rays. Okay, so the whole process really boils down to this four-step sequence. I like to think of it as a kind of cosmic slingshot. First, emission. We boil the electrons off the cathode. Second, acceleration. A massive voltage yanks them across the vacuum tube at a huge fraction of the speed of light. Third, deceleration. They slam to a violent stop as they crash into the anode. And finally, production. That abrupt stop forces the electrons to shed their kinetic energy, and they release it as high-energy photons, which we call X-rays. Now, why does mastering all this physics matter so much? Well, it's because these photons have this incredible ability to pass right through soft tissue, but not through dense stuff like bone. And that gives us a window, a way to see right inside the human body. And this just brilliantly shows how versatile one simple principle can be. From a standard X-ray to check for a broken arm, to a real-time fluoroscopy that lets us watch a joint in motion, all the way to a complex CT scan that builds a full 3D model of our organs, every single one of these technologies is powered by the exact same physics inside the X-ray tube we've just been talking about. Of course, having the power to generate ionizing radiation, well, that comes with an equally great responsibility to use it safely. Understanding and respecting the principles of radiation safety is without a doubt non-negotiable for anyone in this field. I absolutely love this quote from Nobel laureate A.H. Compton because it's such a great reminder that while we have very clear rules and protocols, at the end of the day, a thoughtful, common-sense approach is what matters most. It's not just about following a checklist. You have to understand why the rules are there in the first place. And that why really boils down to these three core principles. I want you to remember these three words: time, distance, shielding. Get your work done efficiently to minimize the time of exposure. Get as far away from the source as you practically can because the dose drops off dramatically with distance. And always, always use proper shielding, like lead aprons and screens. These three things are the absolute foundation of keeping both patients and practitioners safe. So this is really the key takeaway for today. A deep understanding of the physics, from the thermionic emission all the way to radiation safety, is what allows us to confidently and safely use the power of X-rays for an immense amount of good in the world. So I'll leave you with this final thought. The X-ray tube was a monumental leap forward, no question. As you continue on with your studies, I want you to think about what the next leap is going to be. What's the next revolution in imaging? And what part might you play in it? That's all for today.